Thanks.
Okay, so let's start the morning session. The first speaker is Jason Fan from the Chinese University of Hong Kong, Shenzhen. He will tell us principal elements and fermion boson harmonic oscillators. So please start.
Thank you. Thank you. Thank you for the invitation. And I apologize for I'm a little confused where to go. So I checked with the colleague. He is in a class. So then I will be able to finish the whole contents of what I can say. Okay, so what's the purpose of doing this? Is related to the quantum of Fourier transform. So let me start with the story from very beginning. So the talk will be divided into the three parts. First is we recall the definitions of the principal elements. This was basically defined, studied by Bertrand constant. Advisor, so I know him very well. Yeah. The second part is how this is related to the Fourier transform in a way it is kind of define a unit, kind of a universal frame operators on all unitary representations. So this is the second part. The third part is combined with the analysis on the superspace. So how those Fourier transform actually correspond to Hamiltonian element, how this goes to the superspace. Let's go to the first part, principle. So what do we mean principal elements? So I will start with the very beginning. So let G be a simple, simple or it can be semi-simple, but for convenient, just assume this is a simple Lie algebra over C. This can be extended to other Lie algebras. Well, any other field, algebraic closed field, but that's just the sake. Okay, we have the Cartan subalgebra and root vector decomposition. G is the adjoint group, so we take G to be the adjoint group. Later, we will do the real forms and possibly the representation has to go to the coverings. Yesterday, Daniel talked about coverings. Okay, so what is the most important element for us? Is this so-called row check. So what is row check? Row check is the element in the Cartan subalgebra such that it pairs with all the simple roots equals 1. So this is the parent. So root is in the dual space. Yeah. So this element is in the Lie algebra. So we pick up this particular element. Yeah. This is what I mean. The place rule of the Hamiltonian when we deal with all kind of representations. And the most direct way, the far the quickest way to directly define the principal element is the following: is we just pick up the to write P as exponential of this corresponding row check. It's but it's not immediately exponential row check. You have to write a 2 pi I divided by a s. In other words, this had to be put in a proper coefficient. You can consider the y prime the subgroups time t, but a particular value plays the important role. And this s in the denominator is called Coxeter number. Yeah, so I will get this number. Number important to us. So you think this is just some element in Cartan subgroup. Okay, so the property for that is the conjugacy class of that is consists of all the so-called principal elements. So we see the principal element because this is in the same conjugate class. And people familiar with the SL2 theory, this is corresponding to the principal SL2. In other words, it's the nilpotent element corresponding to the largest nilpotent orbit. Anyhow, we use the principal SL2, the SL2 embedded into G, the Lie algebra G. So we restricted the adjoint representation to this principal SL2. It decomposed into irreducible representations of SL2, and it's we know this representation has to have the zero weight, so its dimension is 2m1 plus 1 plus all the way. There are m irreducible representation of SL2, and the dimension 2mi plus 1 is called this mi called exponent. This number also this is also an important invariance for the Lie algebra. So Constant showed the following. He said if R is a regular element, in a sense, it's first it's semi-simple and all the eigenvalues are different, and assume the K is the order of this regular element could be infinity, and then the minimum possibility is this S. And if in case this regular element has order S, if and only if the principal as we just defined. So this is a characterization to describing this regular element. In other, the principal element. In other words, it's the among all the regular elements such that it has the smallest possible order. I give you a reference. It's the 1959 American Journal of Mathematics. Okay, so how about the Coxeter element? Coxeter element is a particular element in the Wall group. So we're considering the reflections in the root system. So you use write down all the simple reflections, write down a product to get an element. But if you change the order, it gives you different element, but they all conjugate. So the Cox element is kind of special among the same conjugate class that are conjugated by the Wall group. So the principal element also corresponding to it's corresponding to the Cox element, but not in the original Cartan subgroup. See, because we have the P is it's the inside of the Cartan subgroup, so it's if it's X on the Cartan original Cartan subalgebra, it will be trivial element. But if you change to the other element is called, so while we're describing this H prime, it became the Coxeter group for the other corresponding. So this is the constant so-called in A population. So let me describe in the other, the H prime. H prime is not the deal. It's the different Cartan subalgebra. So what is this? Okay, so the story is need a little bit of notation, but doesn't matter. You know the way to define it. So I put it in a way it's maybe the shortest in written, but maybe not the most convenient way to remember. So we use this principal element P. It's coming from the fixed Cartan subalgebra. So how do we define the other one? Either we fill first to a gradation and get the corresponding eigen space, and then you can be able to define the other H prime, H prime there. In any case, this is called Cartan subalgebra in a position to H with respect to P. So you don't need to all go through all the check all the every details here, but you know the way to define is kind of opposite Cardan subalgebra. And if you opposite it twice, it's get back the original H. So this is the way to define this. The reason I already mentioned, because P is in the corresponding Cardan subgroup, so it's cannot just it acts on the Cardan subalgebra trivially. So we are doing a different one. Okay, so here is the table about the exponents. This Chevalier first determined all the exponents for the classical group ABCDE. Yan Zhida, when he studied in France, he determined all the exceptional cases. So this is the exponents. So the corresponding Cox number was listed on the very right column. You see, this number is interesting. It's always even, except for the first case is if n is even. That case is SL2n plus 1. If n is even, then that is odd integer. So all the other cases are even. So we will use this to divide it by 2. This is the idea. Okay, so we write a W sub 0 to be the longest element for the Wire group. And except for that special case, we can take in the powers of the principal element by this Cox number divided by 2. And this is the very element we are interested. It's lifting. It's the lifting of the longest element. That's what we are considering, because this gives, I use the F because this gives you the universal way of defining the Fourier transform. We'll get to this. So the idea is the lifting, and the lifting of Wire group elements has been a intensive study by many people, including George Lustig, Jeff Adams. So this is the lifting of the by the lifting of the longest element in particular case. Okay, so let's also treat the case this special case. You cannot divide it by 2. In this case, you can still write down explicitly the lifting of the element. So right, that's the you can this very explicit way. That case, you are not writing explicit as the power, but you can still get a different. Okay, so let's get to this Fourier element, Fourier element F. So it's X on the Cardan subalgebras as the longest element of the Wire group. Its square is 1. It's very easy to check the definition. So if it's not the adjoint group, this could be some root of unity. But why we call it the Fourier operator? Because this is indeed for the interesting cases, this gives you exactly the corresponding operators in the as classical Fourier transform. I will get to this. Okay. Yes. That's right. I will get to the real groups. Yes, I will get to the real forms, because that element, what's important is even for the complex group, you can regard it as a real group. And this is the corresponding exact element. I have not talking about representations. Typically, it's axon unitary representations. This is the only element in the group, and it plays the role as the universal Fourier transform. So we will get to this. but before we get to that, it's worth to understand this element better to describing this. So this corresponding involution, because it's a square adjoint representative of f is a square equals 1. So it's the introducer involution. So this corresponding to the so-called quasi-split real form. And the way to define this, people already studied, is there was some equivalent conditions to describing. So if the case is not ADE, you know, the null auto-automorphism in that case, it's not a ADE, then the quasi-split is really just giving you the split group. In other words, the longest element of the wire group actually introducing the split real form. But I consider that as an operator in the group. Yeah, so we will get to this. But for the other cases, there is a way to describing this element. It's there were the equivalent conditions. If this any element T is conjugated to this adjoint representative of F, if and only if its values satisfy that condition. So in general, if you have arbitrary element in a group, it's always larger than this value. Yeah. So somehow it's also taking the minimum possible value. That's the way to describing this particular element. But again, this is a complex group. We have to go to the real case. Let me also telling you there is another way to do the lifting. Yeah, this is called the Tits group or TC extension of wire group of some cross sections. Yeah, so there is some other ways of describing this. I'm giving the reference to considerance. The way to define this is following: is we have to fix a pinning. Pinning basically is so a Borel Cartan subgroup and fix a choice of the root vectors, positive root vectors, and this is called pinning. Fix that, then you have a way to define the reflection reflections. Yeah, this is the reflections of wire group, but are lifted to the normalizers, and a expression like this for the simple is independent of the choice, independent of the reduced expression. As long as you write this as the shortest expression, this is independent of that. Yeah. So this is another way to define the lifting. This is called a Tits lifting. Okay, so now let's get to your question. We will talk about the real groups. The first real group, of course, we can do this free operator to many kind of real form, but the most interesting case for us is the split real form, compact real form. Yeah, the split real form is the one so that the Cartan subgroup at the connected component, which is A vector group. The other one is just Z2, copies of Z2. And so you can think these normalizers as the extensions of the connected component, A part. The other is connected, the connected component, the different connected component corresponding to the pi 0. And this way of defining this is exactly corresponding to the T extension groups. So for the T group, there is this natural topological way of realizing the normal subgroups. So the split group, for the split group, we can have a natural way of defining the normalizer. So the lifting will be natural. The same thing you can, so we will define this. So now I want to specify to a particular case is you think there will be a there will be this Z2 component, and the different signatures will giving you a different lifting, and this is different lifting is also square. In the complex case, square equals identity. So this gives you the different real form. So for example, if we are in a type A, it's having UPQ, different real form. So I'll get that. Actually, symplectic group is my main example. Okay, for compact group, it's easy because we have the maximum torus, and then the variables is just the normalizer over this centralizer, which is just maximum torus. In that case, the Fourier operator is defined unique up to the conjugation. But for the split real case, there could be different conjugated class. It's may not be unique. It's can come with a different real forms. So the reason is you have this quasi split involution, but you can twist it with other. Okay, so this is exactly reflected into the classical Fourier transform. If we define classical Fourier transform, remember this is defined by integration. But this integration, we have to pick up this inner product on R. If this is a standard inner product, we get this standard Fourier transform F. But if this is defined by a bilinear forms or inner product with a signature, then this would become a different Fourier operator with the but it can also be written as exponential of something. You see, there will be some corresponding Laplacian operator with a pairing operator, and that's things usually corresponding to Laplacians with something a potential. This is the corresponding to the Hamiltonian. Usually people call this Hamiltonian. Yeah. So I have not talked about the groups. This is the classical case for the Fourier transform on Rn. But this can be realized as a particular representation for the symplectic group. So this is the idea. Okay, so now we look at the group actions on that. So we define the symplectic groups is the one which preserves, is all the 2n by 2n real group preserve the symplectic form, and there is this particular element on the it's zero on diagonal, but anti on the other part is IPQ and minus IPQ, and this particular element, when it acts on the particular element representation called oscillating representation, it exactly gives the Fourier transform as we just defined in the previous slides. Let me recall. So previous slide we defined the Fourier transform by integration, but when you consider the oscillating representations of all the L2 functions on Rn, precisely is actually Schwarz functions. Yeah, because we have a differentiation. Schwarz functions, you get a corresponding element is exactly the one coming from this IPQ. So there is also another case, special case, is when this n, SP2n means real rank is n, but it's coming from 2n by 2n matrices. If this n is also even, so we're talking about the SP4m case. In that case, there will be another. You can define the Fourier transform by a skew symmetric bilinear form. Remember the Fourier transform we defined. We are using a bilinear form, a pairing. If you use a skew symmetric, non-degenerate skew symmetric, that we require n to be even. In that case, we also get a symplectic Fourier transform. That's corresponding to that element. It's also exactly the same. IPQ with the P equals N, Q equals 0 with some kind of twisting. So this is also an interesting, very interesting case. Okay, so let me go to the the decompositions of the Fourier operator. This coming from the so-called the classical invariant theory and Hall dual pairs correspondence. Yes.
Excuse me. Please use the microphone connected on Zoom so that the question is understood for people on Zoom.
I usually Fourier transform can be defined based on the representation, I think.
That's right. So
But,
when we have
really, I cannot find which one is the representation in this context.
yeah, in this representation, there's something called the oscillating representation, oscillator representation, or the wheel representation. You never heard of that?
Oscillator representation on that symplectic.
On the L2 functions of all the Rn, you can realize this as the representation of the symplectic group. Okay, so let me explain this. This is extremely important. This representation is coming from the quantum mechanics. Actually, this was first studied by I.M. Siegel. Siegel, he was the advisor of Bertram Constant. So when I was studying at MIT, he was also a professor there. So David Morgan, Bertram Constant, and I.M. Siegel. So he's my advisor's advisor. I also know him quite well. So Siegel was the first studied this representation. So this called at MIT. They called a Siegel representation. So he's the first one. Siegel. So, but later people called it Siegel-Shell wheel representation. Why is Shell? Shell's thesis was also writing details about this. Yeah. So how he studied this is the first you study the representation for the Heisenberg group. So the Neumann theorem says if the Heisenberg group, the irreducible unitary representation of Heisenberg group have the same central character, it must be equivalent. And the symplectic group is the automorphism group of the Heisenberg group. So it induces a representation. It's not very directly defined, but anyhow, we can write the representation explicitly on this. So you think about L2 functions of Rn, but you think this is the Schwarz space. So there are two kinds of operations. So this is exactly I'm going to explain. How do you define this representation? So wow algebra. So wow algebra is the differential operators with the polynomial coefficient. I will write this in a very abstract way, but you can think this V is just Rn, and is V star is just using a inner product identified with Rn. So you can let differential operators just by taking derivatives and the variable itself by multiplication acts on the Schwarz functions of Rn. That exactly defines this representation. But the symplectic algebra is the things of order 2. So you can construct it explicitly, although the very original one from the Siegel V and Wheel representation will define this for arbitrary field. Yeah, so the Siegel and Wheel and the Shell studied it from quantum mechanics, of course, is over R. And so you can have the very straightforward construction. Okay, so the classical invariant theory has two parts. It's first called the first fundamental theorem, and then the second fundamental theorem is about its relations. By understanding that, there will be a duality. So you study the invariant of G, and it's generated in a very nice case, generated by the other Lie algebra G prime, and then you get a dual pair correspondence. For example, in the case we just described, this is symplectic group. There was ON-SL2 dual pair, and also UPQ-U1 dual pair. in the case n is even, there will be also symbolic case of dual pairs. So what do I mean? The dual pairs, the symbolic, the oscillating representations of the symbolic group, and these subgroup subalgebra actions decompose into multiplicity free irreducible representations, so you get a correspondence. Okay, so the simplest case is the spherical harmonics. I think many people know this. Is you consider all the polynomial function, algebraic functions, you decompose that into the functions of different degree, pk, and then you have the harmonics, and its orthogonal complements. Orthogonal complements can be describing as x squared times pk minus 2, degree minus 2, and so on. So you get this decomposition. So this is the very first examples of the dual pair correspondence. Yeah. So the functions can be written as the harmonics and the invariance and harmonics. The invariance is the ek harmonics hk, and the actions can be written explicitly. The harmonic hk would be a irreducible representation of OM, and ek would be the SL2 representation with lowest lowest weight. This is the infinite dimensional. Lowest weight is k plus 2 OM. So this is not exactly SL2 group representation. It's the two-fold cover representation, the Lie-algebra representation. So then the Fourier transform, the operators on L2 of M is also decomposed. Yeah. Let me first describing the most obvious decomposition is those functions you consider the length subspace is the polynomials. It decomposed into the degree k from constant, degree 1, degree 2, and so on. And the representations also the Fourier operator corresponding to the actions on this representation. And the actions is given by polynomial degree k is actually x by some kind of a scalar. So this Fourier operator, because this also defines the involutions on the symbolic group, is corresponding to the fixed point is the UN, is the maximal compact subgroup. So now you decompose this, each of the pk is exactly the k types, the UM, the irreducible representation of M. And its center is exactly this U1. Yeah, center is U1. So center acts on those irreducible representations by a scalar. That scalar is x is exactly I raised to the power k plus n divided by 2. And even you can do the UPQ. For the UPQ, the decomposition is more complicated. It's called a later representation. And the action also given by its center of UPQ. For the spherical harmonics, the decomposition is related to this so-called Hankel transform. So I will give you the reference. The paper I will student, former student. It's called a Journal of Fourier Transform and Application. Okay, now let's get to the super space, because I think I'm running out. Yeah, I have probably 10 minutes. So let me go to the.
Yes, you have 5 minutes.
I have 5 minutes. Thank you. So we have this super space case. Yeah, so super space case is basically we have some commuting variable and anti-commuting variable. So for the commuting variables, we get the symmetric functions, but in order to do the differentiation and in the L2 space, so I write of S. S is the Schwarz space. on the anti-commuting variable, we know this is the Grassmannian algebra or the exterior algebra. So the functions, algebraic functions on that has two parts. One is this symmetric variable, the other is the anti-symmetric variable. So yeah, so my friends are Henrik the B, and he has a friend, he has the teachers, students, and colleagues. They have done quite a bit of work on this. Yeah, so so there will be the superspace, but of course there are many other people studied this. So I was describing this Fourier transforms on that. So Fourier transform on that is the for the metric variables, as we see, we will call it boson, and the exterior algebra part of it called fermion. And for the fermion part, you can also define in a way very looks like classical way. That's either called a Baranzin integral. It's not really integral, but it's a kind of operation very similar on this finite dimensional space. And the Fourier operators define a similar way. It's a square is up to a scalar, and it's related to the star operations on the exterior algebra. It's called Hodge duality. And as the case for the oscillating representations, polynomials functions divided in the polynomial of odd degree and even degree. That's two irreducible components of oscillating representations. In this case, if we look at the operations of symplectic of spin groups R of n, it's also splitting into two pieces. It's exactly two half spin representations. It's the exterior algebra of even degree and the exterior algebra of odd degree. There was also restrictions on the UN as a subgroups of SPN 2n plus 1, and you have decomposition. And the corresponding element, of course, is the one lifting of the longest element for the SP spin 2n for the compact groups. So let me also repeat this. The similar pictures as Weyl algebra to describing this half spin representation by Clifford algebra, and the Clifford algebra. People are familiar with maybe just I'm just using a basis. It's a straightforward way to define this, and this is the endomorphism of exterior algebra. So that's how we construct the spin representation, and the spin groups is the inside of the Clifford algebra. And you see this Clifford algebra can be written as the super tensor algebra. This is exactly as for the symplectic case. The oscillating representations can be decomposed into the SL2 representation. SL2 tensor cross SL2 cross SL2. This is had a very similar way of defining this. Okay, so let me conclude by saying that with also classical series about the invariant series, but this is called a skew invariant series. Because this, we are not doing the symmetric algebra, we are doing the skew symmetric algebra. There will be also the correspondence, very similar series. So there will be duality. In the case, I just describing this natural duality of UN actions. But if this is a 2n even things, then there will be symplectic space structure. Then you can decompose this in a natural way by the SP2n and SL2 duality. I think that was here. Thank you very much for your patience.
Oh, thank you very much.
Thank you.
So, are there any questions or comments?
I think there are so many experts in our side.
Okay.
I hope. Okay.
Can I ask a question?
Yes, yes.
Okay.
Great.
In the final part, you explained the Fourier transform on the superspace. I expect that the relevant Lie algebra is Lie superalgebra. Is it true or?
Let me try to understand your question.
In your final slide, you just write SP2N symplectic group, not Lie superalgebra.
Oh, sorry, you SP2N. You talk about the which one?
Yeah, I'm asking about
the symmetrical or anti-symmetric case. You asking the symmetric case or anti-symmetric case? Exterior algebra.
I expect that in the superspace case, we have both symmetric and anti-symmetric.
Oh, symmetric case.
No. On superspace,
anti-symmetric.
You have both.
Both symmetric and anti-symmetric. Yes.
And I expect the relevant Lie algebra is Lie superalgebra, not ordinary. But in your last slide, you just presented S.
That's right. Yeah. So if you treat this representation as a big group, yes. Yeah. But somehow, if I only look at the Fourier transform, I can think this is the representations of the symplectic group SP2MR cross the actions of the spin SP2N, spin 2N. So I would considering the two smaller groups. Yeah.
I mean,
yes, you're right. This space maybe can be put in a even larger representation. Larger group could be a super.
I expect some OSP group, super group.
That's right. That's right. But inside of that group, there will be a G0 subgroup, which is the symplectic group cross the orthogonal group.
I see. The bosonic subgroup contains SP. Yes.
That's exactly correct. Yeah. So the Fourier operators coming from that subgroup.
Okay. Thank you.
Because for the Wire group, essentially the Fourier operators, Fourier actions is coming from the Wire group. Even for supergroup, I think the Wire group would be defined with respect to the G0, the even part.
Okay.
I'm not sure. Did I said it? So to consider the Fourier operator, we actually only need the even part of the supergroup.
I see.
Thank you for the question. Yeah, so this is a very insightful question.
Any other questions?
Yeah,
Could I ask a question? So still I could not understand. So in quantum information, people consider something like the non-commutative Fourier transform, but in that case, people consider wild Heisenberg group. So based on
consider what group?
Wild Heisenberg, wild Heisenberg group representation. Wild Heisenberg.
Heisenberg. Why?
Yes, Heisenberg representation. So usually people consider non-commutative Fourier transform over the Heisenberg representation.
Yeah.
But you didn't consider so.
Yeah, well, actually, I prepared the two slides. I don't have time. Yeah, so thank you for asking this. Yeah, you see, I have some syntax. Yeah, as when we do the quantum information theory, we have starting from the bits and go to the probability bits and then go to the qubits.
Not the qubit case, not the qubit, bosonic case, bosonic.
Neumann. Oh, you are not talking about
bosonic system, not the qubit.
Not qubit. For Neumann.
No, bosonic system, boson system.
Oh, bosonic.
Yes.
Bosonic means the original, the classical Fourier transform. Because I'm not sure what do you mean?
Yes, bosonic system we often consider Heisenberg representation, and we discuss the Fourier transform over the Heisenberg representation.
Okay, yes, but the symplectic group is the automorphism group of the Heisenberg group.
I know, but the Heisenberg much simpler.
Heisenberg algebra is simpler, but the theory is richer in the semi-simple, semi-simple groups. Yeah, you see by coming from the var algebra actions, the symbolic algebra
But
structure.
already quantum information people established the Fourier transform over the Heisenberg group.
Yeah, but if you wanted to do a uniform way of Fourier operator, that is not enough. Yeah, I'm talking about the very general reductive group, the Fourier transform for any representation. It's not just the particular Heisenberg one.
I want to know how to reduce the Heisenberg group Fourier transform over the Heisenberg.
That one is exactly the special case I told you. Yeah, you see, this is the Heisenberg group Fourier transform can be exactly written like that. That's the Fourier transform. It's exactly the classical transform if you consider the Heisenberg algebra action. Yeah, that's the most important part. I agree. But this is the beginning. Yeah.
But
if you want to,
in that case, Heisenberg Fourier transform written as different form, not this way. We form it different way.
It's equivalent.
No, different. In that case, non-commutant Fourier transform is different from this
form. Fourier transform, let me tell you, the Fourier transform is the function, is the transform from space, from the functions of one space to the functions of its dual space. But if you have a pairing between this V and V star, then you would get the integration.
No, what do you say? Not function. In quantum Fourier transform, considered as a function to the different matrix.
Hold on. You're talking about quantum Fourier transform or Fourier transform. We have to pin down the Fourier transform for the Heisenberg algebra or Heisenberg group or some quantum Fourier transform. This is for different.
No. Say quantum Fourier. In the quantum information theory, people consider different way. We formulate quantum Fourier transform over the Heisenberg group.
Excuse me. Since we are behind the schedule, please continue your discussion after the session. Okay.
So yeah. Okay. So let's discuss maybe outside.
I'm very sorry.
Yeah. Thank you.
So let's thank the speaker again. Thank you very much.
Thank you.
So please stop the sharing the screen. The next speaker is Iwane-san. Are you ready?
Okay. Share my screen. Okay. Okay. Yes.
So the second speaker is Takumi Iwane from Nagoya. He will tell us vertex Lie by algebra. So please start.
Thank you for the introduction. It is my pleasure to speak at this workshop. In my talk, I will introduce a new algebra, which can be regarded as a vertex algebra analog of a Lie by algebra. It's called vertex Lie by algebra. Okay. The contents of today's talk are as follows. To To begin with, I introduce vertex algebras and some related notions. Vertex algebra consists of the following data: space of states and vacuum vector, translation operator, and state field correspondence. An important property of the vertex algebra is the operator product expansion, as follows. At first sight, it may look complicated, so I will present a typical example in the next slide. Let G be a Lie algebra with symmetric invariant bilinear form. Then we can consider its affinization. It is an infinite dimensional Lie algebra, and it's a Lie subalgebra. Then we can consider the induced G-hat module. Then it denotes Vg. Vg is itself universal affine. Vg is itself vertex algebra, and for any parameter k, we can consider its quotient vertex algebra. It is called the universal affine vertex algebra of level k. This construction can be generalized to vertex Lie algebras. Vertex Lie algebra consists of the following data. Note that the state field correspondence concentrates on the polar part. For vertex Lie algebra, we can construct the universal enveloping vertex algebra. For example, vertex algebra has the vertex Lie algebra structure, and the algebra and with symmetric invariant bilinear form, then we can define a vertex Lie algebra. So then we have a universal affine vertex algebra as universal enveloping vertex algebra. Regarding the classical theory, in view of PBW filtration, the universal enveloping algebra can be thought of as the quantization of Gay star. Gay star has a Poisson structure. So we want to think of vertex algebra as a quantization of a kind of Poisson algebra. In other words, we want the classical version of vertex algebra. Indeed, the structure of classical version of vertex algebra is known as the vertex Poisson algebra. So we want to understand what vertex Poisson algebra is. It is known how to construct a vertex Poisson algebra by Arakawa. For commutative algebra, we can consider the jet algebra, which is regarded as an Nag space. In a geometric point of view, the jet of Poisson algebra is not only a commutative algebra, but also carries a vertex Poisson algebra structure. Next, we consider the jet of the coordinate ring of Poisson Lie groups. Before proceeding, in this talk, a Lie group means affine algebraic group. An affine algebraic group can be regarded as a commutative Hopf algebra through its coordinated ring. Moreover, if G has a Poisson structure, then coordinated ring is forms Poisson Hopf algebra. For example, if G is semi-simple affine algebraic group, then it has a Poisson Lie groups structure. So let's consider the jet of Poisson Hopf algebra. Poisson Hopf algebra, since Poisson Hopf algebra is a Poisson algebra, so jet is vertex Poisson algebra. Furthermore, Hopf structure induces three structure. Coproduct and counit is homomorphism of vertex algebras, and antipode is merely a linear map. So this discussion leads us to a vertex Poisson Hopf algebra. Vertex Poisson Hopf algebra consists of the data V is vertex Poisson algebra, and the counit and the coproduct is homomorphism of vertex Poisson algebras, and antipode is merely linear map. Although S is a linear map, the following identity holds. Now, we've obtained the notion of vertex Poisson Hopf algebra, and we regard it as vertex analog of Poisson Lie groups. Since vertex Poisson algebra has a commutative Hopf algebra structure, we can consider its Lie algebra as follows. So, for example, if V is a jet algebra of the coordinated ring of a Lie group, then its Lie algebra is the formal power series in coefficient with gay. Furthermore, the algebra of vertex Poisson algebra, vertex Poisson Hopf algebra should carry a structure induced by state field correspondence y minus z. So in order to capture the induced structure, we import some technical assumptions as follows. Indeed, this assumption is not strong. Indeed, the jet of the coordinate ring of finite dimensional Lie groups and its the associated Lie algebra satisfy the assumptions. Then this finite part, Lie algebra is a polynomial with coefficients in gay. So then we can obtain the induced map. For this coproduct, delta z, we can verify the list vector has a vertex Poisson algebra and the compatibility condition. For example, gay is Lie bialgebra and L is polynomial with coefficient in gay. Then the coproduct in a sense of vertex-Lie algebra is explicitly written. So we have a abstract definition of vertex-Lie algebra is the algebra with derivation and product such that LT delta forms vertex Colli algebra and compatibility and satisfies the compatibility conditions. Okay, finally, I would like to introduce the quantization problem. Recall the story of quantum groups. Quantum groups carries quads, triangular Hopper algebra, and in this context, the elements of R is called the universal matrix, and the corresponding equation is called the Yang-Baxter equation. Then its classical limit to Q to 1 nor H bar to 0. Then algebraic structure. Then its algebraic structure induced by R is co-boundary Lie bialgebra. So in this talk, I've introduced the vertex Lie bialgebra. And in fact, I've defined the co-boundary vertex Lie bialgebra. Thus, it is natural to ask about its quantization in analogy with the theory of quantum groups. This is the problem I'm currently working on. Okay, ちょっと早い。Okay, thank you for your attention.
Okay, thank you very much. Yeah. So are there any questions? Comments? Okay, so is it true that you first introduced our formulated vertex Lie bialgebra? Is it your original work?
Oh, yeah, yes.
Oh, then may I ask a question? What is your motivation to introduce such a new algebra?
Its motivation is so firstly, I've considered jets of Poisson Hopper algebra. So I know the jet of Poisson algebra is vertex Poisson algebra, and so Poisson Hopper algebra. For the Poisson Hopper algebra, what is the jet? Then and vertex Poisson Hopper algebra we got it as algebraic group. So what is the tangent algebra? Then so this is my motivation. Yeah. Sorry.
So you just consider
Yes.
tangent space.
Yeah.
Do you have some application in your mind?
No.
I mean,
I want
you just
to.
formulate it just very abstractly.
Yes. So now I try to find application. but I don't have any idea.
Okay, thank you. Maybe it's better to have some application to your rather abstract formulation.
Yeah.
So any other questions? From people on Zoom? No? So let's thank the speaker again. Thank you very much.
Thank you.
So the next talk will start at 10:50 in China time and 11:50 in Japan time. Okay, so we have 10 minutes. We have 10 minutes break.
Put it up. Okay, okay. Yes, yes. I want to discuss.
岩根さん、共有を切ってもらえますか。
Hello, Professor Lee. Are you ready?
Yeah. Yeah.
Okay.
Okay. So
Let's resume the morning session. The next speaker is Qin Lee from Shastek. The title of his talk is Geometric and Deformation Quantization of Kähler manifolds. So please start.
Okay, thank you for the introduction, and also thank you for the invitation to give a talk here. So this is the outline of my talk today. Consists of the following parts. So I'll start from the basic definition of canonical quantization and Dirac axioms, and then also deformation quantization, geometric quantization, and then our work on quantizable functions and differential operators. And the last part will be applications and further questions related to our recent and also ongoing work. Yeah, so let me start from the so-called Dirac quantization axioms. In quantum mechanics, a classical phase space X is replaced by a Hilbert space H. The vectors in this Hilbert space H describe the quantum states of this mechanical system. And in the procedure of quantization, classical observables or smooth functions on this phase space X are quantized to operators on the Hilbert space, capital H. And it should satisfy the following Dirac axioms. So this assignment is linear. That's the first requirement. And the second one is the constant function 1 should be mapped to the identity map of this Hilbert space. And the third one is the most important one, is the I of H bar, that's the formal variable, times the operators corresponding to the Poisson bracket of two functions f and g should be equal to the commutator of the corresponding operators f hat and g hat. So this is called Dirac's axioms. So there is the notion of canonical quantization. So let me give you the example here. The canonical quantization of the flat space R2n, or you can equivalently think of that as the cotangent bundle of Rn. That consists of the following very explicit procedures. So first, the Hilbert space, capital H here, HC, C stands for canonical. That's the L2 function on Rn. So you can see that it's not the function on the whole space R2n, but only depends on half of the variables. So it's the functions on Rn. And then the canonical, the coordinate functions are quantized to the following operators. So you have Qi hat acting on F. So F here is a function on Rn. So that's simply the multiplication by Qi. And then you also have this Pi hat, and then that's the up to a constant, that's a differentiation of a function F with respect to Qi. And these operators satisfy the commutation relation. So you take Qi hat, the commutator of Qi hat with Pj hat, it's a constant times delta ij. And so if you have a function which are actually polynomials in PIs, can be quantized to the so-called normal ordering prescription. So you have a bunch of Q's and a bunch of P's, and here we have a finite condition on these P's. So what you can do is that you can push all these P's to the right-hand side, meaning that they first act on functions on Rn, and they act as differential operators. So you can see that this finite condition is equivalent to saying that in the differential operators, we need it to be of finite order. Okay, and on this R2n, there is actually a mathematically equivalent quantization procedure called the Bachmann-Fock quantization. So here we use a different identification of R2n. We identified with the complex space, Cn. And then there is the Bachmann-Fock quantization, which is equivalent to the canonical quantization. So the Hilbert space here, capital this capital H, BF stands for Bachmann-Fock. So that this vector space, this Hilbert space consists of holomorphic functions on Cn, which is L2 integrable with respect to the Gaussian metric. You can see the explicit formula here. And then the quantization for coordinate functions, you can see that it's similar to the formulas in canonical quantization. But now you replace those Pi, Qis by these holomorphic and anti-holomorphic functions respectively. For instance, here you have a holomorphic function Zi, and then the corresponding operator Zi hat is simply Zi times 2 times f of z. And then if you have a anti-holomorphic function, that plays the role of a differential operator. And they also satisfy the commutation relation similar to the one on the previous page. And also similarly is that for functions which are polynomials in Zi bars, the quantizations can be defined via a normal ordering procedure. Namely, you put differential operators first and then you multiply. Now, the deformation, these two pictures of quantization, the canonical quantization and Bachmann-Fock quantization, they give rise to two star products on R2n, which are called Moya-Weil product and also weak product on R2n. I think in the previous talk by Professor Huang, it's also mentioned this Weil algebra thing. And so they satisfy the following formula. So you have two functions here, f and g, and then you turn them to operators with denoted by f hat and g hat. You take the composition, and it's equal to the operator corresponding to f star with g. So this star can be the Weil product or the weak product, depending on the quantization you are choosing, either the canonical quantization or the Bachmann-Fock quantization. So there is actually a more general notion of deformation quantization of symplectic manifolds. So given a symplectic manifold, M omega being its symplectic structure, then a deformation quantization of M is an associative product star on smooth functions such that f star g equals, so here you have actually a power series expansion in the h bar's power expansion. So you have the first term is f dot g, that's the classical commutative product. And then you have high order terms, where these CIs are bidifferential operators. In particular, the first one, in the first one, you can see actually the Poisson bracket. So C1FG minus C1GF equals the Poisson bracket of F and G. So this actually reflects the first order non-commutativity of this star product. Yeah, I should say, so there has been extensive mathematical study on deformation quantization on symplectic manifolds, or more generally, Poisson manifolds, by the celebrated conservative formality theorem. And there is also a general method called the Fedotov quantization. So there, on a symplectic manifold, there exists a so-called Weil bundle, defined as follows. So this is the completed symmetric product of cotangent bundles with this formal variable h bar here. So there is the fiberwise Moya product, or on a Kähler manifold, you can choose the weak product. And a compatible flat connection known as the Fedotov flat connection. So So the smooth functions, smooth functions on this phase space X is in one-to-one correspondence with flat sections under this connection. Yeah, so in a joint work with Ryan Grady and Sili, we can show that the Fedosov quantization is actually equivalent to the BB quantization of a one-dimensional Chern-Simons theory, which we constructed on a general symplectic manifold. Now, there is also another method of quantization known as the geometric quantization, or the Coulson-Soriot geometric quantization. So this procedure goes as follows. So first of all, you need a quantum condition. That's a integral condition that the cohomology class of this symplectic form is actually integral. So which guarantees the existence of a complex line bundle L with a Hermitian structure and Hermitian connection such that the curvature associated to this connection is -I times omega. And the so-called pre-quantum Hilbert spaces is defined as the L2 sections of this pre-quantum line bundle, and it's tensor powers. You can take the positive tensor powers of L, then you define the so-called pre-quantum Hilbert spaces. And so in this quantization picture, we not only need the Hilbert space, but we also need to know what operators act on these Hilbert spaces. So for every smooth function, the Coulson-Soriot pre-quantum operator is defined as follows. So we denote it by F tilde. So that consists of two parts. The first one is F, although I put it on the right-hand side, it's the multiplication. And then the second one, you can see it involves the formal variable H bar here. So you actually need to take the evaluation that H bar is the inverse of the tensor power K. So sometimes we call this the quantum level. And then times the connection of this Hamiltonian vector field associated to the F acting on a holomorphic section. So you can easily check that this assignment from F to F tilde satisfy the third Dirac axiom. Namely, you take the commutator of F tilde and G tilde and up to a constant, then that's the operator corresponding to the Poisson bracket of these two functions. Now, so in this in the Coulson-Soriot geometric quantization picture, it's very important that we need to choose a polarization on this phase space. So there are different choices. You can choose a so-called complex polarization, or you can pick a real polarization. And then the Hilbert spaces are defined. So in this scalar case, we choose the complex polarization, or equivalently, a complex structure making X a Taylor manifold. And then the Hilbert space is defined as the holomorphic sections of the tensor power of L. And this is the HK. Now, so you might wonder why you pick this. You need this polarization. So roughly, you want the canonical quantization and also the basic examples of canonical quantization and Bachmann-Fock quantization to fit in this picture. And you can see that in those pictures, when we take Hilbert spaces, usually it only depends on half of the variables on this phase space. So a complex structure actually makes this possible because on X, this X, if it's complex, so you have holomorphic functions and anti-holomorphic functions. So holomorphic functions is just half of them. So you pick the holomorphic sections, and that plays the role of picking half of the variables. Now, so there's so you want this function f. Now we have seen that it satisfies the third Dirac axiom, but then we need this operator F tilde to act on this subspace of holomorphic sections, then the problem is that only for a very limited class of functions on X, the corresponding pre-quantum operators actually preserve this subspace of holomorphic sections, namely the Hilbert spaces. So that is to me a main problem in this picture, and that's also the reason we only call these operators pre-quantum operators instead of quantum operators. So one solution is the following analytic definition of Berzin-Toeplitz quantization. So these are defined on a pre-quantizable Kähler manifold X in the following way. So the Hilbert spaces is the same as before, namely you take the space of holomorphic sections of L to the power tensor power K. And then given any smooth function, so there is a recipe defining the Berzin-Toeplitz operators. So it's defined by this simple formula. So given a holomorphic section, you first multiply it by this function f. Now, so it's not holomorphic. In general, it's not holomorphic anymore. And then what you can do next is you can consider the orthogonal projection to the subspace of holomorphic sections, because they are naturally defined inner products, and then you can do this orthogonal projection. And if you look at the asymptotic behavior of the composition of these operators as this tensor power K goes to infinity, so that's how you take the asymptotic behavior. So K goes to infinity, and that actually gives you a deformation quantization of this Kähler manifold X. Now, so this is these are the general pictures of this story here. So let me mention some open problems in quantization. So first one is in geometric quantization, we need a polarization, and deformation quantization. We know that so roughly deformation quantization should act on Hilbert space as operators. So is there a role of polarization in deformation quantization? So in mathematics, we usually require compatibility conditions. Now that we know deformation quantization should act on geometric quantization, and then so it's natural to see this compatibility condition here. And the second one is in geometric quantization. Is there a quantum operator extending the cosensorial pre-quantization operator? So as I just said before, so given a function f, you have multiplication and then plus a constant times the the connections, actually the covariant derivative using the Hamiltonian vector field of the function f. So, or equivalently, how do we quantize classical observables? So, of course, the Berzin-Toeplitz operators or Berzin-Toeplitz quantization is one way to solve these problem, but it's not clear how it's related to Cousin and Soriot's originally defined pre-quantum operator. And the third question is, why is there a locality in the composition of two Berzin-Toeplitz operators? And then the fourth open question is, how do the Hilbert spaces and operators depend on the choice of polarization? Because the symplectic structure actually comes from the the physical structure of the classical system. But then in the quantization picture, we need an additional mathematical structure known as the polarization. So you'd better have a quantization which should be independent of this choice of this mathematical structure of polarization. So this is, and in some cases it's known. I mean, there are the so-called hitching connections, which can naturally relate the quantization on the different choices of polarizations, but in general, this is unknown. Yeah, so let me start with some of my works. this is some background. So the L infinity structure on a Kähler manifold is described by the following operators given in the following theorem by Karpranov. So it's a little bit complicated. So I just listed here. And the main point is that if you this dk here gives actually a differential, so that means dk squared actually vanishes. So with this vanishing, so you can define the cohomology. You have a differential, and so you have a cochain complex. You can compute the cohomology. And the cohomology under this differential dk is actually isomorphic to OX. That's a sheaf of holomorphic functions on this Kähler manifold. So in other ways, this gives a cochain complex model for the holomorphic functions. Now, on the other hand, so this is so Karpranov's result is in some sense classical. It's not quantum yet. Now, on this Kähler manifold, there's also this complexified Weil bundle. So in Karpranov's original picture, you only involve this completely symmetric product of the holomorphic cotangent bundle. But we can also involve this anti-holomorphic cotangent bundles. And then we have this, you take the tensor product, we obtain this complexified Weil bundle. So in a joint work with Conor Liang and Kuo Chen, we proved the following theorem. So for every star product on X, there exists a Fedosov connection on this complexified Weil bundle, such that the associated star product is exactly this the given star product. And more interesting is that this Fedosov connection is a quantum extension of the L infinity structure in the sense that if you restrict df on the subbundle of holomorphic Weil bundles, so you can see the complexified Weil bundle consists of two parts. One is the symmetric product of holomorphic cotangent bundle, and the other part is the symmetric product of anti-holomorphic cotangent bundles. So if you restrict to half of that, it's exactly the Karpranov, the connection defined by Karpranov. Now, so the first result is so the Fedosov quantization via this quantizing or quantum extension of Karpranov's L infinity algebra structure is actually compatible with the complex polarization. So actually, in this deformation quantization, we can already see how the polarization actually comes into this picture. And we can do this BV quantization machinery. We can do certain Feynman graph computation. And if you try to compute the partition function in this Feynman graph computation, it only involves only tree level and one loop level graphs. So in other words, we get a so-called one loop exact BV quantization of the Kähler manifold X. And this actually greatly simplifies the computation. And so far, we do not have a fully understanding of why this happens. So it's just by explicit computation. So what we expect is that the superconformal structure, the n equals 2 superconformal structure on this X actually is the main reason for this one loop exactness. So this is actually in sharp contrast with the general symplectic structure, in which the BV quantization actually involves all loop quantum corrections. And only in some very rare cases you have this one loop exactness. For instance, there's this holomorphic Chen-Simon theory by Kevin Costello, and for a sigma model from S1 to T star Y, that's the cotangent bundle of a smooth manifold by Ryan Grady and Owen Gwilym. Yeah. So so the next thing we want to say is so on Kähler manifold we do not only have Weil bundles, but we also have something the Weil bundles actually acts on. So this is some module structure for the while bundle. That's called the Bugman-Fogg bundle. And the idea behind this approach to Fedosov's deformation quantization is actually very clear. So you start from some linear algebra, and that's the fiber-wise star product on the while bundle. And it describes the local picture of star products. And a Fedosov flat connection actually gives you the gluing data for a global star product. So how it glues these local pictures. So in this Bugman-Fogg bundle picture, we follow the same line of thought in this construction. We start with the fiber-wise Bugman-Fogg action of the while bundle on this holomorphic thing. So that's only the completely symmetric product of the holomorphic cotangent bundle. And then we need a connection to glue these local pictures. Now the Fogg bundle is not only this Wx here, but you have to take the tensor product of certain twisting, which is exactly the pre-quantum line bundle and its tensor powers, depending on this quantum level k here. And so our theorem is that there exists a Fedosov flat connection on this Fk of the following form. So you can see that it's actually very similar to Fedosov's original connection. The only difference is that you replace the bracket using with respect to the while product by this Bugman-Fogg action here. And it turns out this cochain complex, so this df square is also 0. And so you have a differential and cochain complex. It turns out it's closely isomorphic to the sheaf of holomorphic sections of L to the tensor power of K. So in other words, we also have a cochain complex model for the Hilbert spaces in the cosensorial geometric quantization picture. Now, so why is this interesting? Because in these pictures, you can see that we actually have a picture which combines deformation quantization and geometric quantization together. So it's possible to quantize a classical observable or a smooth function f to an operator on this Bugman-Fogg bundle for the following two reasons. So for every function and every holomorphic section, we can let OF act on OS. So OF is the flat section associated to this function f, and OS is a flat section corresponding to this holomorphic section S here. And then we can do this fiber-wise Bugman-Fogg action. So you can see that it basically consists of two parts. You have a linear algebra part, and then you also have a geometric part, which actually glues these linear algebra picture. And there is actually a compatibility between the Fedosov connections on both the while bundle and the Bugman-Fogg bundle. So the output of the above action should also be flat. And so the output of this function of OF acting on OS gives you another holomorphic section. So that gives you the operators acting on the Hilbert spaces. Now, however, this ideal picture only happens for a class of functions, which we call quantizable functions. So it's a little bit, it might be a little bit confusing, this quantizable functions, because I have seen in the literature many different quantizable functions, so defined by different mathematicians. For instance, in Cosensorial's original picture, people also call that quantizable functions. But actually, there are too few of those functions. So here, what we define here is how you actually have enough such functions, at least in the sheaf theoretically. Now, the reason you want quantizable functions in general, OF is a formal power series expansion of these H bars. But in the Bugman-Fogg action, you need to take the evaluation, say H bar equal to 1 over K. So there is an infinite sum in this action. So you need certain finiteness condition to make sure that you get a well-defined action. Now, so once you have a quantizable function, so say f here is quantizable, then this Fock action, Bachmann-Fock action is well-defined, and which corresponds to a holomorphic section of L tensor K. And also, it's easy to see that since OF and OS only depends on the jets. So if you look at locally, stalkwise, then you can see that actually the fiber-wise, so you have it only depends on the infinite jets of F and S here. So you actually have a differential operator. So in other words, we have obtained an assignment from quantizable functions to holomorphic differential operators. So this is the picture. This is something you can do after some simple computation. And another thing I want to say is that I have actually mentioned in the previous page that because you have certain locality, these quantizable functions actually form a sheaf on this X. And locally, these quantizable functions actually is dense. You use the correct notion, and it's actually dense in the space of smooth functions, meaning that we actually have enough quantizable functions. Now, the interesting thing, a little bit surprising result, so we obtained is the following. So if you have a quantizable function, so we have two ways to quantize it. So one is the Berzin-Toeplitz operators we call TFK. So it's defined, as I mentioned before, is first you multiply a holomorphic section by a smooth function, and then you do the orthogonal projection. So this is analytically defined. And then the right-hand side is more algebraically defined differential operators, as I just mentioned before. So given a quantizable function, you actually have a holomorphic differential operator on sections of L to the tensor power K. So you can see they are defined in very different ways, but turns out that they are equal to each other. So this is something a little bit surprising, because another way to see why this is a little bit surprising is that for a function, the Berzin-Toeplitz operator associated to this function, it's you cannot expect it to be local, because differential operators are local. And this one, TFK here, you do not expect it to be local at all. But turns out if F is quantizable, then this equality here tells you that the Berzin-Toeplitz operator associated to this F is actually local. So that's something you do not expect from the definition. Yeah, so let me say some applications and some further questions. Now, in this picture, we actually restrict ourselves to Kähler manifolds. In other words, we are using the complex polarization. So is there a similar picture for real polarization case? So is there a similar construction of quantization of functions to differential operators? Is there a notion of quantizable functions? So that is also very interesting, and also possibly related with the Atiyah-Singer index theorem. And the second one, there's a super version of Kähler geometry called super Kähler geometry. There are also super functions instead of smooth functions on ordinary manifolds. For instance, you can pick the right super Kähler manifold, and you have differential forms on a Kähler manifold. Those are super functions. So roughly you have a commuting part and an anti-commuting part. So I think this is also mentioned in Professor Huang's talk. And in this case, we can also try to quantize these super functions to operators. So is there a similar picture of these quantizations? And the third interesting application and possible future project is Gukov-Witten picture. So they propose a new quantization scheme called brain quantization using ideas and tools from two-dimensional sigma models and mirror symmetry, A models in mirror symmetry. So is it possible to study brain quantization using the differential operators we constructed here and how it's related to mirror symmetry? Yeah, so these are what I want to say, and I'll stop here. So thank you very much.
Okay, thank you very much. Any questions, comments?
Can I have a few questions? Can you hear me?
There is a question from Nagoya.
Yes. No. Yes. But yes. No reaction. 聞こえてない。
Please wait.
Yeah.
Can you hear me? Okay. It's okay. Yeah, I'm Shintaro Yanagida at Nagoya, and thank you for your very interesting talk. And I have a few questions. And the first is that you mentioned that the quantization is one loop exact.
Mm-hmm. Yes.
Could you explain a little bit the details of this?
Yeah.
Exactly.
So let me put it in this way. So in this graph computation, so basically, the graph computation involves vertices and the and also the edges. So the edges are labeled by the so-called propagators, and these propagators consist of the pairing in this Kähler structure. So it involves the so in this pairing you have one side. So edge consists of two parts, right? So it's like one side to one vertex and the other half. So it consists of two half edges. So one half edge is labeled by holomorphic things, say Zi, and another half edge is labeled by Zj bars. So it's anti-holomorphic. So the reason you have one loop exact is because in this connection, so let me put into this picture. Yeah, so in this dk, and actually we quantize it to df. So in this dk here, you can only see, yeah, so in this dk here, you only see those sections of complete symmetric product of cotangent bundles. And then when you quantize that, you take the endomorphism part, so you also have a holomorphic cotangent bundle. But then using this Kähler structure, you turn the tangent bundle part to a anti-holomorphic cotangent bundle. So it's like you have many degrees. So you have many degrees of these holomorphic cotangent bundles, but only degree one in anti-holomorphic cotangent bundle. So when you do these, this graph computations, you will see that there's this symmetry that only. So it's actually a very simple graph computation that only one loop is possible, because if you have two loops, then you need higher degrees of these anti-holomorphic cotangent bundle parts. So roughly that's the reason you only have one loop part.
I see. And you also mentioned that a similar phenomena appears in
Sorry?
the William and Grady one-dimensional Chern-Simons.
Ryan Grady, you mean?
Yeah, Chern-Simons theory in the Chern-Simons theory.
Chern-Simons theory. Yes. So let me put into the page.
The space, I think.
So I think that's before, yeah. Yeah, so this one here, yeah.
Yes. Yeah, Chern-Simons.
Yes.
Yeah, it is. Yeah, there are some similar phenomena, but is there some conceptual reasons for one loop exactness?
Okay, so in this work there is also a one loop exactness, but so the one loop exactness in this in the work with gradient Sli is we have one loop exactness on the cohomology level. So it's so if you try to compute the contribution of higher loop, I mean those at least two loop levels, and then you will see that you compute the cohomology, and then you can see that it's actually exact, meaning that in cohomology it vanishes, but on the cochain level, I mean it doesn't vanish on the nodes.
I see.
But in this scalar picture, it's you can just see the vanishing of the on the cochain level. So that's a difference here. Yeah.
Oh, very interesting. Thank you very much.
Okay, thank you.
May I ask a short question? In your
Yes.
slide, we see one-dimensional Chern-Simons theory.
Yes.
I think the standard Chern-Simons theory is three-dimensional. What do you mean by one-dimensional Chern-Simons theory?
Yeah, so we actually use the name of Chern-Simons theory because in this work we actually constructed a one-dimensional field theory by writing down.
You mean spatial dimensions one and time one, and you actually one plus one dimensional?
No. It's not the dimension. It's just if you write down the Lagrangian of this classical field theory, and it looks very similar to the three-dimensional Chern-Simons theory. So that's the reason we give it the name Chern-Simons theory, one-dimensional Chern-Simons theory.
I mean, in the case of three-dimensional Chern-Simons theory, the integrand is just a three form. And then in your one-dimensional case, what is the integral? Just one form?
Just one form, because the space-time is one-dimensional.
Yeah,
so you have
actually.
Yeah, and then you integrate on S1.
So you integrate one form about one-dimensional space.
Yes, on S1, yes.
Yeah. Thank you. Are there any questions?
Sorry, I have quite elemental question. So you introduce some existence, so many results. So what is your main result in this talk?
So the recent result. So the recent result is the last theorem here. So let me put it here. Yeah. So this is some main theorem here. Yeah.
L means you. L means you.
Yes.
Okay. Other questions? From people online? No? Okay, if not, let's thank the speaker again. Thank you very much.
Thank you.
So the next talk will start at 11:40 in China and 12:40 in Japan. So we have maybe 7 minutes break.
Can you hear me?
Yes, yes.
Yeah.
May I share my
Oh, yeah,
slide?
of course. We have maybe 5 minutes, right? But
Okay,
you can share the screen.
okay. Can you see my slide?
No, not yet.
Okay. Not yet.
No. It seems being processed, but
Okay.
you can see.
なんか真っ黒い画面が共有されてます。で、ユースケ西中が画面共有を開始しましたってちっちゃく表示
ミラーリングをしてるつもりなんですけど、できてない。
それが入ってないですね。はい、
じゃあ、ちょっと違う方法で。
もう一度多分最初からやり直してもらった方が。
はい。これでどうですか？
ちょっとまだダメですね。
ダメですか？違う方法を試しましょう。
あ、出ました。OK です。
これでます。
Okay, let's resume the session. The last speaker in the morning session is Yusuke Nishinaka from Nagoya. The title of his talk is Costello-Gaussian Factorization Algebra and Vertex Algebras. So please start.
Thank you for the introduction. I'm Yusuke Nishinaka from Nagoya University. Today, I will talk about relationship between two notions, factorization algebras and vertex algebras. These two notions have their origins on physics, especially quantum field theory. Costello-Gaussian factorization algebra encodes the algebraic structure of observers in field theory, and vertex algebras are known as an algebraic framework for two-dimensional conformal field theory. And two-dimensional conformal field theory is a kind of quantum field theory, so we expect a natural relationship between factorization algebras on the complex plane and vertex algebras. In fact, Costello and Williams give a general method for constructing vertex algebras from factorization algebras. And they also construct factorization algebras corresponding to the affine vertex algebras and the beta gamma vertex algebras using what are called factorization envelopes. Since the affine vertex algebras and beta gamma vertex algebras are both realized as enveloping vertex algebra of vertex D algebras, so it is natural to try to generalize their construction to vertex D algebras. In other words, we want a construction of factorization algebras starting from vertex D algebras in a way that make this diagram commute. Today's goal is to explain this construction. So let me start with a brief introduction to factorization algebras and vertex algebras. Let X be a topological space and M a symmetric monoidal category. Symmetric monoidal category is simply a category with a tensor product, like the category of linear spaces. Prefactorization algebra on X with values in M consists of the following data. First, map F that assigns an object of M to each open subset U. Second, for each inclusion of open subsets, morphism FUV, which we call the extension morphism. These two pieces of data form a precursive. Prefactorization algebra is then a precursive together with morphisms FUBW called factorization product for each open subset U, V, W, such that U and V are disjoint and both contain the larger open subset W. Factorization algebra is a prefactorization algebra that satisfies a kind of local to global condition similar to Siev's, but I'll skip the details here. And there is an important class of factorization algebras called locally constant. The fundamental result about them is that there is an equivalence between locally constant factorization algebras on Rn and En algebras. In the case n equal 1, this means a categorical equivalence between locally constant factorization algebras on the real line and associative algebras. Next, let me explain factorization envelopes, an important way to construct factorization algebras. First, note that if category M is additive, then the category of digitally algebras is symmetric monoidal under the direct sum. So let M be a symmetric monoidal additive category and take a prefactorization algebra L with values in digitally algebra. Now consider the Chevalier-Lenberg chain complex of a digitally algebra. This gives a symmetric monoidal functor from digitally algebras to chain complexes. By composing with L, we obtain a new prefactorization algebra. This is what we call the factorization envelope. Expressly, the Chevalier-Eilenberg chain complex is the symmetric algebra of the shifted space A1 equipped with a derivation DCE. This differential is the sum of the one coming from the differential of L and the one induced from the Lie bracket of L. Using factorization envelopes, we can construct the factorization algebra corresponding to the enveloping algebra of a Lie algebra. So fix a smooth manifold N and consider the compactly supported drum complex. For Lie algebra J, this map gives us a prefactorization algebra with values in digitally algebras. Applying the factorization envelope, then produces a prefactorization algebra with values in chain complexes. Now let's look at the case where M is a real line. By taking homology, we get a prefactorization algebra with values in linear spaces, and it turns out to be locally constant. So therefore, the space of global sections carries the structure of associative algebra, which is isomorphic to the enveloping algebra of K. Now let's move to vertex algebras. Vertex algebra is a linear space V equipped with a special element called the vacuum and a linear map Y called the vertex operators, which together satisfy these actions. A typical example of a vertex algebra is the affine vertex algebra. Let J be a finite dimensional simple Lie algebra and fix a symmetric invariant form kappa, which is just a scalar multiple of the king form. Then considering the affinization of J by kappa, the vacuum module V kappa J has the structure of a vertex algebra as follows. This is what we call the affine vertex algebra. An important action of a vertex algebra is the locality action, which implies OPE of operator product expansion of vertex operators. As you can see, to compute OPEs of vertex operators, it is convenient to introduce the lambda bracket. If we axiomatize the property of lambda brackets, we arrived at the notion of vertex Lie algebras. Here is a basic example. Let CURJ be the tensor product of polynomial ring with finite dimensional simple Lie algebra K. This linear space becomes a vertex Lie algebra with a structure given by this lambda bracket. Moreover, for a given symmetric invariant form kappa, CURJ admits one-dimensional central extension denoted by CUR kappa K. As we saw from the introduction of vertex Lie algebras, vertex algebra naturally gives rise to vertex Lie algebra. This construction defines a functor which has the left adjoint. The vertex algebra BL obtained this way is called the enveloping vertex algebra of L. To construct BL, we first define a linear space L as this quotient space. This space L inherits a Lie algebra structure from the lambda bracket of L. We call L the current Lie algebra of L. Next, this linear subspace D plus L is a Lie subalgebra, and BL is defined as the induced representation of the trivial representation of D plus L. For CUR kappa K from the previous slide, the corresponding current Lie algebra is isomorphic to the affine Lie algebra, and the corresponding enveloping vertex algebra, where we identify the action of the central element K as the identity, is exactly the affine vertex algebra. Now, let me explain the relationship between factorization algebras and vertex algebras. To produce vertex algebras from prefactorization algebras, we need some functional analytic tools. There are several possible approaches, but here we use phonologies, which are axiomatization of boundedness. Let BVS be the category of complex phonological vector spaces. This category is pre-abelian, so consider the category of chain complexes of complex phonological vector spaces. And to construct vertex algebras, our prefactorization algebra needs to be equivariant under the natural action of the isometry group on the complex plane. For an open disk DR, since the disk is invariant under the rotations, we can define the subcomplex FDR delta by using the action of S1. Then if F satisfies the condition called amenably holomorphic, the direct sum of its homology carries the structure of the graded vertex algebra. Now let's construct the prefactorization algebra corresponding to the enveloping vertex algebra. Let X be a complex manifold and consider the compactly supported Dolbeault complex. For a vertex Lie algebra L that is at most countably dimensional and a morphism of sheaves D, we define a complex LXD as a certain quotient. This gives a prefactorization algebra on X with values in the category of DG Lie algebras. Now let's focus on the case where X is the complex plane and D is partial DZ. In this case, if L is n-graded, then this naturally becomes equivalent prefactorization algebra. Applying the factorization envelope, we obtain equivalent variant prefactorization algebra FL on complex plane with values in chain complexes. Finally, let me state the main theorem. Suppose integrated vertex 3 algebra L satisfies the following two conditions. The first, each L delta is finite dimensional, and second, there exists an integrated linear subspace E such that L is linear isomorphic to this tensor product. Then the prefactorization algebra FL is amenably holomorphic, and the corresponding vertex algebra is isomorphic to the enveloping vertex algebra of L. This theorem applies, for instance, to CURJ. For its finite dimensional central extension CUR kappa J, we use the twisted factorization envelope. And in this way, we recover the result by Costello and Graham. And moreover, this construction can be generalized to any integrated vertex 3 algebra L satisfying these two conditions with a 2 cycle omega. That's all. Thank you for your attention.
Thank you very much. Any questions, comments?
Sorry, could you give me the definition of the vertex 3 algebra?
Vertex 3 algebra, okay. So I did not write the complete definition of vertex 3 algebra. Vertex 3 algebra, but it is vector space to B and equipped with linear transformation T and the lambda bracket, which satisfies certain conditions like the algebras.
I could not understand. So, the vertex 3 algebra is a kind of real algebra or kind of some extension?
Vertex 3
finite
algebra.
dimensional.
Vertex 3 algebra is vertex algebra analog of real algebra, so it's a kind of real algebra.
Kind of.
Yes, it's
finite dimensional vector space.
Not it is not necessary to be finite dimensional, but it's it is vector space 3 equipped with lambda bracket. This lambda bracket is satisfies the axiom like Jacobi identities or skew symmetry.
So sorry, I'm not so familiar. What is the definition of the vertex algebra?
Vertex algebra is vertex algebra is linear space B equipped with the element vacuum and linear map Y. This is called vertex operators and satisfies some actions. And if we define the lambda bracket using this NS product, then vertex algebra becomes a vertex 3 algebra.
Sorry, could you go back to the definition of vertex algebra?
Vertex algebra.
Still, I could not understand. So,
Mhm.
A tensor B maps to Y
B tensor V.
A. What is this?
Y is a map from B tensor B to the space of Laurent power series with values in B. So we the image
G
of
is a kind of a variable. So,
yes. This is a
Laurent
variable.
expand.
Yes. So the image of A tensor B can be expanded in this form.
So I'm confused because why is the map V tensor with something? That's Laurent expansion. But next you consider A tensor B maps to Y. I'm very confused. Why you write down in that way? Because the inside of Y is the input of Y should be some two elements, should be A and B. No, I'm quite confused.
Okay. You ask about this notation, right?
Yes, it looks like quite strange.
This is just a notation. So we so yeah this is
Why
just
has
a
the input? Why has the input of V tensor V?
V tensor
From
V.
the
So
result.
V tensor V is represented here and here, and we express the variable z here. So I know it's quite confusing, but
I think it's just a matter of notation, right?
yes. It's
You define Y bracket AZ by left right hand side.
yes.
And so I'm confused. V is vector space, and the A is element of V.
Yes.
And that A has a subscript A. I'm very confused. V is linear space, and that element has a subscript n integer, and n run to the minus infinity to plus infinity. I'm sorry confused. What is
an. So this expression is image of A tensor B and Y. So the image is in the space of Laurent series with values in B. So we can expand in this form. So this is
It's just a linear map.
Yeah.
Linear map, so we can expand in that way, right?
yes.
I'm quite confused. What is AN? A subscript N.
N
Why
is
is already defined.
A and B is coefficient of the Laurent series expansion. So this is in this is an element of B.
Element. But A N B is already defined.
A and B is coefficient of this Laurent series. So this is an element of B.
This one is canonically defined. I'm very confused. So because A and B is element of vector space, and
Yes.
the product is something like defined, but I don't know this is the product algebra or not. Also, there is some element an with some coefficient or some element. I'm very confused.
So, okay, you can understand vertex algebra is linear space V equipped with infinite many product A and B. You can understand vertex algebra in this way.
Ayasan, is okay or can you stop the discussion? Okay, it's over the time. So let's thank the speaker again. Thank you very much.
Thank you.
So this is the end of the morning session. The afternoon session starts at 1:30 in China and 2:30 in Japan. So see you.